deals with the notion of NP completeness. We'll study this notion and we'll see how to use this notion effectively. The first thing I'll sort of talk about is motivation. Okay. Hopefully at the end of this, I'll motivate you sufficiently that you'll be interested enough to study about this subject. Okay, so imagine that you finished your BTech, you have done all your subjects well, and then you've gone for an interview. You have, you land your dream job. The company pays well, you're really happy, you've settled in. It's a software job. You're very happy because you have to deal with designing things, and the boss is also very happy with you, and he wants to give you challenging projects. The first project you get is the following. Okay, it's scheduling jobs on computers. So your input, the set of jobs, and each job has a size associated with it. Okay, so let's say the jobs are J1, J2 up to Jn, and the sizes are S1, S2, and so on up to Sn. These sizes could vary. Some of the jobs could have the same size, some could have different. You can think of them as positive integers. Okay. Now there are two processors. Okay, so there are two processors, P1 and P2. Both are identical, and your job is to schedule these jobs on these two processors. Okay, so you want to automate. Your boss wants you to automate this process. You have to write a program which takes input these sizes S1, S2 up to Sn. So let's say from an array of size n, or reads it off a screen, and you have to schedule these jobs on processors P1 and P2. Now the scheduling should be such, okay, that the last job finishes fastest. Okay, so what do I mean by this? Supposing I schedule all of them on P1, the time taken will be S1 plus S2 plus S3 and so on up to Sn. Okay, let's say that a job of size Si takes the same time Si to finish. Okay, if I schedule it, it takes time Si. Also assume that there is no preemption. Once you start a job off, it has to run to completion. Okay, so if I run all of them on one processor, the time taken is S1 plus S2 plus S3 up to Sn. So at time S1 plus S2 up to S3 and so on up to Sn, all jobs will finish. Now supposing I schedule the even jobs on P2 and the odd jobs on P1, let's say S1, S3 and so on. Okay, here it's S2, S4. Let's say there are 7 jobs, okay, S5, S7, S6. So this is how the jobs are scheduled. Now the time taken on P1 is S1 plus S3 plus S5 plus S7. Time on P2 is S2 plus S4 plus S6. Now it may so happen that these are very large jobs. Okay, let's say these sizes are 1 and these are 100. Okay, then the time at which the last job completes is 300, right? This processor finishes off in 4 units of time, while this takes 300 units of time. So the last job finishes after 300 units of time. This is not what you want. So you want to sort of distribute the jobs evenly among these two processors, right? So you want to distribute the jobs in such a way that these large jobs, say one of the S4 should be here, okay, and maybe S5 should be here, and so on. Okay, you want to distribute them as evenly as possible. Okay, so you think about this for some time, and here is the first algorithm you come up with. Okay, so you take the jobs in order. Okay, so the jobs are of sizes S1, S2, and so on. Okay, put the first job in the first on the first processors. Okay, here's P1. I put S1 here. Okay, the second job goes to P2. Now you put when I take the third one, you put it on the processor which is least lightly loaded. Okay, for instance, if S1 is greater than S2, then I put S3 here. If S1 is greater than S2. Okay, and you keep doing this. I look at S4 and I see which one is greater. Assume that S2 and S3 are on P2. Check whether S1 is larger than S2 plus S3 or is S2 plus S3 larger than S1. If S2 plus S3 is larger than S1, then I put S4 on P1. Okay, so S4 will go here if S2 plus S3 is larger than S1. Okay, you can break ties as you want. This is the first algorithm you come up with. You code this and it starts working, your boss is happy. Okay, but the next day the boss shows up and tells you that this does not work. Okay, so he gives you an input on which you produce a schedule which takes some time t. Okay, so you take some time t while the boss produces a schedule which is less than t. Okay, so the optimum schedule on the input is smaller. Okay, the total time that the optimum takes is smaller than the time that your algorithm produced, and the boss says fix this. Okay, so at this point I would like to give you an exercise. Give an example to show that this algorithm does not produce an optimum schedule. Okay, so give an example. To show that this algorithm does not produce an optimum schedule. Okay. Well, you go back and you figure out that there is something wrong with the algorithm, in the sense that if these jobs are mixed up, if the sizes are mixed up arbitrarily, maybe that's the reason the algorithm doesn't work. Okay, so here is your next attempt. Okay, this is your next attempt. The first thing you do is you sort the jobs by size. Okay, now you know that S1 is less than S2, is less than S3, and so on. Okay, you know that the jobs are in increasing order of size, and now you do the same algorithm. You put S1 on the first processor, S2 on the second, and so on. Okay, well, this seems to work, but 2 days later again your boss shows up with an example which doesn't work. So let's look at this example. Okay, the example has 5 jobs, and the sizes are as follows: 2, 2, 2, 3, and 3. Okay, let's see what your algorithm does. So here are my 2 processors, P1 and P2. So these are the job sizes. So the first job goes on to P1. The second job is on P2, right? The third job you could put either on P1 or on P2. Let's say we pick P1. Okay, the next one goes here, and well, 4 is smaller than 5, so you put the last one here. Okay, now the total time that your schedule takes is 3 plus 2 plus 2, which is 7. Okay, on this processor, of course, you take 5 units. On this, you take 7 units. So the total time to finish all jobs is 7 units. But you can see that this is not optimum. The best way to do it is, I guess you've seen this by now, you put the 2's on one processor and the 3's on the other. Now this takes, sorry, there are only 2 3's. Okay, I'm sorry about this. There are 2 3's, so this takes 6 units and that takes 6 units. Every job is finished in 6 units of time. So this algorithm that you have come up with also does not work. Okay, let me again repeat the algorithm. You sort the jobs by size. Okay, now you look at these jobs one by one and assign these processors greedily, in the sense that you put the first one in the first processor, the second one the second, and when I reach the ith job, you put it on the least lightly loaded processor. Okay, you sum up the previous sizes which are on each processor, choose the smaller one, and put this new job on that processor. Okay, this was the algorithm we came up with, and this does not work. Okay, here is an example where it doesn't work. Okay, so now what do you do? Well, you can go back and try and fix this example. Okay, maybe you come up with another heuristic which beats this example, but I can tell you that it's extremely difficult, possibly impossible, to come up with a smart heuristic like this which does well for all inputs, okay, which always does well. So you, after trying various heuristics, most of them don't work. You are now at the end of your patience. You're really worried about your job, because the boss is now threatening you with dismissal. So then what you do is this. Okay, so you now sort of want an algorithm that works always. Okay, so what you do is a brute force algorithm. So take every subset of the jobs. Okay, so I have jobs, I have sizes S1, S2 up to Sn. So take all subsets. Okay, so let's say S is S, say subsets S. So compute the size of S and size of S bar. Okay, S bar is the complement of S. So all jobs not in S, which is S bar. So essentially you want to put S on processor P1 and the complement on processor P2. Okay, so you do this and look at the maximum of these two. Okay, and choose the maximum of these two. So this will tell you the time, the total time that this schedule took. Okay, so do this for every possible subset and pick the minimum. Okay, take all subsets, compute these, choose the maximum, and of these maximum, pick the minimum. Okay, of these, you can easily see that this will always give you the right answer. Okay, because you will look at all possible ways of scheduling these jobs on two processors, and one of them has to be the minimum. Now this is fine, this algorithm works. Your boss tries out a few inputs and it works for almost all, in fact for all inputs, till your boss feeds in an input with, let's say, 1,000 numbers. Okay, there are 1,000 jobs which have to be fed to these processors, these two processors. So he gives the input is a list of size 1,000. Now you start running the algorithm. 5 minutes pass, an hour passes, 2 hours, 10 hours, 1 day. The algorithm doesn't stop. 2 days, 1 week, and now your boss is starting to get worried. Here is an algorithm which has worked for all small inputs, and now it's the weak and the algorithm has not stopped. Okay, for an input of size 1000. Well, I can tell you that this is not going to stop even after many years. Okay, you can take years and years and this is not going to stop. In not my lifetime, not your lifetime, maybe many lifetimes. That is the problem with such brute force approaches. Okay, let's do a quick calculation to see how much time your algorithm is going to take on inputs of size 1000. Okay. If you have 1000 jobs, the number of subsets of jobs that you look at is 2 to the 1000. Okay, so the number of subsets is 2 to the 1000. Okay. Now, let's assume that in one instruction, a computer can process one of these subsets. Okay, let's see how much time computers will take to process all of these subsets. Now, the fastest computer, okay, runs. Let me make an estimate. Let's say 10 to the 20 instructions per second. This is the fastest computer on the fastest. This is a big overestimate. Okay, it's much smaller than this, but well, we'll assume this. How many computers do you think there are in the world? 10 to the 10, 10 to the 20. Okay, let's say 10 to the 20. This is again an overestimate. Computers in the world. What we are going to do is put all the computers in the world at your disposal to solve, to run your brute force algorithm. So putting these two together, okay, then I have 10 to the 40 instructions I can do in instructions per second using all computers. So I'm using all the computers in the world and I can do 10 to the 40 instructions per second. Okay. So how many instructions do you think one can do in a year? Let's do this calculation. So it's 10 to the 40 instructions per second. So in an hour I can do this times 60. I mean in a minute I can do this times 60, another 60 for an hour, then I have 24 hours a day, and then I have 365 days in a year. So these many instructions a year. Okay. Let me do an overestimate here. This I am going to say is 10 to the 2. This, let's say this is 10 to the 2. Well, 10 to the 2 since we are being generous. This is 10 to the 3. Okay. So number of instructions per year is certainly not more than 2, 4, 6, 10, 10 to the 50. Good. So I have 2 to the 1000 subsets to look at. I can look at most 10 to the 50 subsets per year. Let's see how many years this takes. So let me quickly, so you have 2 to the 1000 instructions, right? And using all the computers in the world, with the fastest speeds, you have 10 to the 50 instructions that you can do per year. Now this 10 to the 50 is roughly 2 to the 10 is 2, 3, let's say, is certainly less than, okay, less than equal to 2 to the 4 times 50. Okay, that is 2 to the 50 for the 200. Okay, so now I just need to divide this by that to check how many years I'm going to take. So the number of years you're going to take is 2 to the 1000 minus 200, which is roughly 2 to the 800 years. Okay, you can check how many particles there are in the universe. This is not very far away from that. Okay, number of atoms in the universe, for instance. Good. So you're going to take a lot of years for this algorithm to finish. This is certainly not what you want to do. If the boss figures this out, you're certainly fired. In fact, even if he doesn't figure this out, you're fired. So what do we do? So this is a motivation for studying NP completeness. So I'll give you a recipe using which you can hopefully save your job if your boss is even a little bit intelligent. So the first part of the course which you did, design of algorithms, was to help you get a job. The second part that we do, theory of NP completeness, will help you keep it. Okay. Okay, so our final objective will be to show that this problem is among hard problems in this world. Okay, what do I mean by hard? It means that so far nobody else has been able to find a solution to this problem. Well, the boss can say, I mean, this problem is just come up with our company. You know, the other companies handle other problems. Why are you saying that this has not been solved before? Well, you can in fact say that if somebody manages to solve this problem, then a lot of other problems which a lot of other people have not been able to solve can also be solved. So this is the kind of statement we would like to make. Okay. Good. So before we formally look at this notion of NP completeness, we'll need a few other fun days. Okay, few other notions that we need to imbibe. The first one is a concept of reduction. Okay, so we'll first look at an example and we'll see what reduction really means. Okay. Yeah, so reduction really means this. Supposing you have a library. Okay, so you have a library where a large number of problems have been, very well coded by a very good programmer. Now, given a new thing that you want to code, it would be very nice if you can use subroutines from the library, okay, in your code, rather than reinvent the wheel and try and do all this by yourself. This is all there is to reduction. How to efficiently use code for other algorithms to generate new algorithms. Okay. So let's look at an example. This is not a very easy example. It's not very hard either. Okay, so before we start, a few definitions which we'll recall. Hopefully you have seen this before. Okay, the first thing is that is the notion of a matching in a graph. G equals VE. Okay, V is the vertex set, E is the edge set. A matching in a graph is a subset of the edge set, is a subset of E. Okay, so let me call this M. The subset M of E such that no two edges share the same vertex. Okay, such that, let me write this down, no two edges in M have the same endpoint. Okay, let's look at an example. So let's take a graph. Okay, let's say this is a graph. Okay, then so here's a matching. The ticked edges form a matching. If I look at these two edges, they do not share an endpoint. Okay, the endpoints of this edge are these two. The endpoint of this edge is these two. They do not share an endpoint. Now, for instance, let me label these A, B, C, D, E. If I take AB, okay, and AD, these do not form a matching. Okay, this is not a matching. Essentially, you want a set of edges so that they look like this in a graph. Okay, they do not share an endpoint. Okay, this is what matching is. The next definition we need is that of a perfect matching. So we'll say that a matching is perfect if all vertices in the graph are endpoints of at least one edge. Okay, is a matching such that all endpoints, I'm sorry, okay, a perfect matching is a matching such that all vertices are endpoints of at least of exactly one edge in M. So it's a matching M such that all vertices are endpoints of exactly one edge in M. So the size of a perfect matching is just half the size of the vertex set. Okay, so then note that size of M is size of V by 2. Okay, so this is a perfect matching. Let's go back to this old graph of ours. Do you think this graph has a perfect matching? The answer is no. Well, there are 5 vertices. Okay, so if I take a matching with 2 edges, I can cover four of these vertices. I cannot cover 5, and I cannot take 3 edges because then 2 of these edges will share an endpoint. Okay, so this graph does not have a perfect matching. Okay. But for instance, if I change this graph slightly, let's see, I have A, B, D, E, and C. Okay, let me add one more. Okay, let's say F. Now this graph has a perfect matching. Right? In fact, it has many perfect. It has at least 2 perfect matchings, maybe 2 perfect matchings. Okay, here's, so I take these 3 edges, AB, ED, and CF is a perfect matching. AD, EB, and CF is also a perfect matching. Okay, the ticks form one perfect matching, and the crosses form another perfect matching. Okay, this graph has 2 perfect matchings. Good. So now that we have defined these 2 terms, here's the problem that we would like to solve. So you're given, so there are 2 problems. Okay, so here is, let me say, one is problem perfect match. Okay, PM is for perfect matching. The input is a graph G, and the question you ask, does G have a perfect matching? Okay, this is your first problem. The input is a graph G, does G have a perfect matching? The other problem we are going to look at is this. It's very closely related to the first one. So this is maximum matching. Okay. The input is the same. Input is a graph G. Okay. The output I need is a matching of maximum size. Okay, so let's look at these two problems. For this problem, I only need to say yes or no. Okay, I just want to say whether the graph has a perfect matching or not. Here, I actually need an output, which is I need to know that I need edges which will be present in some matching of maximum size. We've seen that a matching could have a graph could have more than one matchings of maximum size. Any one of them will do. Okay. Now, supposing in your subroutine library you have a subroutine coded for this, for problem maximum matching. Okay, which so given you have an algorithm so that when you feed in a graph G, it will output a matching of maximum size. Can you use this to solve this problem? The answer is yes. Just feed in the same graph G. Look at this matching. If it has V by 2 edges, V is the number of vertices. If this has V by 2 edges, okay, then the graph has a perfect matching. If it's less than V by 2, then the graph does not have a perfect matching. Okay, so given an algorithm for the second problem, it's very easy to construct one for the first problem. How about the other way around? Okay, which is given, supposing the subroutine has this. Okay, the subroutine library has an algorithm for this, which is given in graph G, it will tell you whether it has a perfect matching or not. And now you want to output a matching of maximum size. Okay, your job is to construct an algorithm which does this, and you would like to use this algorithm, okay, effectively, because this is a very good implementation, and you would like to use this effectively. Okay, let's see how this is done. Okay, so I hope the objective is clear. Let me write this down. So we are given an algorithm for perfect matching. Okay, and you want to design one for max matching. Okay, this is what you want to do. Well, how do you really use this algorithm? So that's the crucial question. In fact, let's take something which is sort of intermediate between these two. Okay, how about trying to find the size of the maximum matching? Okay. If you look at this problem, maximum matching, the output should be edges, a set of edges in a matching of maximum size. Okay, that's what the output should be. Now, supposing we only want to know the size of the maximum matching in the graph. Okay, can we solve this? So let me write this problem down, and we'll try and do this. Okay, so this is objective 1. An intermediate objective is this. Is design an algorithm to find the size of a maximum matching. Okay, so we are given an algorithm for perfect matching. You want to design an algorithm to find the size of a maximum matching in G. Okay, this is how you do it. So you take this graph G. So here is your algorithm that does perfect matching. Okay, here's your algorithm that does perfect matching. Now you first feed in G and ask whether it has a perfect matching. If G has a perfect matching, okay, then you know what the size of the maximum matching is, hopefully. Yeah, it is, if G has a perfect matching, then the size is V by 2, okay, where V is the number of vertices in the graph. Okay. If, so let me write this down, if G has a perfect matching, then the size of maximum matching is size of V by 2. Okay. Okay, so supposing it says that G does not have a perfect matching, now what do you do? Well, yeah, what you do is this, you take okay, you take so here is G. Okay, so step 2, so you take G, okay, add a vertex, this is a new vertex, connect it to all vertices in G. Okay, now call this graph G1. Now you feed G1 into this algorithm for perfect matching. Okay, you've taken G, you've added a vertex which is adjacent to every other vertex in G, and now you feed this into this perfect matching. Okay, again, two things can happen. Either it can come back and say it has a perfect matching, okay, or it can say no. Okay, let's see what happens in both cases. Good. So G1 is G, okay, plus a vertex connected to all vertices in G. That's what G1 is. Now supposing G1 has a perfect matching, then what can you say about G? Well, if you look at a perfect matching in G1, this vertex, this extra vertex, okay, is in the matching it will be connected to something in G. Okay, this is the picture. So here is G, here is the extra vertex. I'm just going to draw the edges in the matching. Okay, so this fellow will be connected to something here in the matching. The other vertices in G are all matched somewhere or the other. Okay, this is if G1 has a perfect matching, then this is the figure. This is how it looks like, which means except for this vertex, if I remove this vertex out, the rest of the graph has a perfect matching. Okay, which means there is a matching of size. This implies that G has a matching of size V minus 1 by 2. Okay, and this is the size of a maximum matching, clearly. We know that because G did not have a perfect matching, it does not have a matching of size V by 2. On the other hand, it has a matching of size V minus 1 by 2. Okay, this is if G1 has a perfect matching. What if G1 does not have a perfect matching? Okay, if G1 does not have a perfect matching, then we know that G does not have a matching of this size. Okay, so then we create graph G2. Okay, so how do we create G2? Well, it's similar. You take G1 plus a vertex connected to all vertices in G1. Now you ask if G2 has a perfect matching, and so on. Then you form G3 and ask whether G3 has a perfect matching, and you stop as soon as the perfect matching fellow says yes. Okay, so let me write the generic step. So you get Gi, the graph Gi is the graph Gi minus 1, okay, plus a vertex connected to all vertices in Gi minus 1. Well, this is how you get Gi. So now you look at G1, G2, G3 and so on, and ask whether G1 has a perfect matching, G2 has a perfect matching, and so on. So let's say K is the first index where the perfect matching algorithm says yes. Okay, so yeah, so which means okay, so assume that Gk minus 1 does not have a perfect matching, and Gk has a perfect matching. Now, what does Gk minus 1 and Gk look like? Okay, so here's my original graph G. For G1, I added one vertex which was connected to everything in G. This was G1. G2, I added two vertices. Now this was connected to this, and it was also connected to everything in G, and so on. So Gk minus 1, I have k minus 1 vertices here. Okay, they are connected to each other and they are also connected to everything in G. Similarly, this is Gk minus 1, and Gk looks like this. I have the graph G and I have k vertices here. Okay, these are connected to each other and they are also connected to everything in G. Okay, there are k vertices which are connected to everything in G. Now this does not have a perfect matching and this has a perfect matching. What does this mean? Now let's look at the perfect matching here. Okay, now yeah, actually I must say that G1, G2 all the way up to Gk minus 1 does not have a perfect matching. So K was the first time that we encountered a graph with a perfect matching. Okay, G1, G2, G3 up to Gk minus 1 does not have one and Gk has one. Okay, so let's look at Gk. So what can a perfect matching here look like? Okay, can it have an edge like this? The answer is no. Okay, why is that? Supposing it has an edge like this in the matching, you remove these two, okay, and this graph now looks like Gk minus 2, right? And this has a perfect matching, but we know that Gk minus 2 does not have. So all edges in the matching must be from vertices here to vertices inside G. Okay, so here's the picture. Here's G. So this is Gk. Okay, these are k vertices. Okay, these k vertices are matched to some k vertices in G. There are n minus k other vertices in G which are matched amongst themselves. So there is a matching inside G, okay, of size n minus k by 2. Okay, so there is a matching in G of size n minus k by 2. Good. And we would like to observe that there is no matching of size larger than n minus k by 2. Okay, this is the largest matching that you can have. Now, why is that so? Supposing, firstly, this has to be even, right? This has to be even. Sorry, the n minus k has to be even because this is an integer, right? So, if there is a matching of size larger than this, that means, so suppose there is a matching of size, let's say n minus k plus 2 by 2, okay, which is nothing but n minus k by 2 plus 1, one more edge, right? So supposing there is a matching of this size, so the claim is that one of the previous graphs, in fact, then g of k minus 2 has a perfect matching. So this will be a contradiction, right? Supposing there is a matching of size larger than this, then g k minus 2 will have a perfect matching. So we'll see this. So here is g, and here is a subset. This is of size n minus k by 2 plus 1. Okay. So here I have n minus these many, which is so n minus n by 2 minus n by k plus 1, sorry, plus k by 2. Okay, that's this size, which is n by 2. Okay, minus and minus plus k by 2. Minus 1. Okay, so let's look at this. Let me just refresh. We are here. Supposing there is a matching of size n minus k plus 2 by 2, then we have to show that g k minus 2 has a perfect matching, right? Okay. So this is g. So it has a matching of size n minus k by 2 plus 1. So the number of vertices in the matching is twice this. Okay. So the size, so number of vertices here, or vertices here, is twice this, right, which is n minus k plus 2. So the number of vertices here is n minus this, right, so which is k minus 2. Okay, this portion has a perfect matching, which was our assumption. So let's look at g k minus 2. So g k minus 2 had g. Okay, this is g. This in fact is g. And I had k minus 2 other vertices which were connected to everything in g and also amongst themselves. Okay, this was g k minus 2. Now what I do is this: I take this matching in this portion as is, and each of these k minus 2 vertices I matched to the other side. Okay, you can see that this gives a perfect matching. Matching on this portion remains the same as in this portion here, and these k minus 2 vertices I match to the other side. Okay, so this shows that g k minus 2 in fact has a perfect matching. Good. Let's recap. We were given an algorithm for perfect matching, and our objective, the intermediate objective, was to design an algorithm to find the size of a maximum matching in G. And what we do is this: we define graphs Gi, okay, where Gi is Gi minus 1 plus a vertex connected to all vertices in Gi minus 1. Okay, we find the first graph. We look at G1, G2 and so on, and we find the first graph Gk which has a perfect matching, which means G1, G2, G3 and so on up to Gk minus 1, they do not have a perfect matching, Gk has a perfect matching, right? Then we claim that there is a matching in G of size n minus k by 2 and no larger. So the size of the largest matching is n minus k by 2. This shows that given an algorithm for finding a perfect matching, I can design an algorithm for finding a matching of maximum size in a graph by calling the other algorithm repeatedly. I don't call it too many times, I call it at most k times here, right? You can actually do it much faster. You can call it faster than k. Okay, so in the following sense, this k can, it can go down all the way up to 4, 5, okay, up to a constant, which means you can call it about n times, right? So we have shown that given an algorithm to find a perfect matching in a graph, I can design an algorithm that finds the size of the maximum matching. Okay, the way you do it is you look at graphs G1, G2, G1, G2 and so on. Okay, find the first graph Gk which has a perfect matching, and the size of the maximum matching then is n minus k by 2, right? If k is 0, it is G, and the size of the maximum matching is n by 2, and so on. If Gk is the first time you get a perfect matching, the size is n minus k by 2. In the worst case, you would call the perfect matching algorithm n times, right? I would call G1, G2, G3, and I can go all the way up to n. Now there is a smarter way to do this using binary search, which I will let you do, which lets you figure out this k in time using only log n calls to the algorithm for perfect matching. It resembles binary search, and it's an exercise for you. But essentially this shows that by calling this algorithm at most n times, I am able to determine at least the size of a maximum matching in the graph. But let's go back now. The objective we had was to find this perfect matching, right? So here, now I have fulfilled this intermediate objective. I can design an algorithm to find the size of a maximum matching. I want to actually find the edges in this maximum matching. How do I do this? Okay. Now, so here's the trick. You take this graph G. So I take G. I find the size of the maximum matching. Okay. So let's say the size is L. The size of a maximum matching. Okay, it's the size of a maximum matching in G. Now what I do is pick any edge in G and remove it. Remove an edge from G, and now ask the same question: what's the size of a maximum matching? If it remains L, then I throw away this edge and I concentrate on the graph that remains. Okay. If it is not, if it decreases, then I put this edge back. This edge is part of a maximum matching. Okay. So I leave this edge. So I look at the edges E1, E2s, let's say up to EM one by one. Okay. When I look at an edge, I remove it and I ask if the resultant graph has a matching of size L. Okay, I find the size of the maximum matching in the resultant graph. If it is L, then I throw away this edge. Okay, otherwise I put this edge back. By the time I am through with all these edges, okay, what I'll be left with is a graph which will be just a matching. It will just be a matching of size L. Okay. Let's do an example. So let's take a simple graph. So here, so let's take a simple graph, E1, E2, E3. The size of a maximum matching here is 2. Okay, I remove E1 and I ask what's the size. Now the size is fallen by 1, the size is 1. So I put E1 back. I remove E2, I ask what's the size is 2. So I throw away E2. Okay. At this point the graph looks like this, because I've thrown away E2. Then I ask for E3, I remove E3 and the size falls by 1. So I put E3 back. So I'm left with E1 and E3, and when I look at the graph that remains, it's a matching. In fact, it will be a matching of size L. Apart from the matching of size L, if there is any other edge, when you remove this edge, the graph will still have a matching of size L. So you will throw this edge away. So at the end of this procedure, what you will be left with is a matching of size L, which is what you were looking for. Okay, so this completes our objective, which we started out with. We were given an algorithm for perfect matching, okay, and we wanted to design an algorithm for maximum matching. What we did first was we designed an algorithm to find the size of a maximum matching, and using this we were able to design one for maximum matching. Right? So we had this in our subroutine library. We added this to the library by using this algorithm, right? And once we had this in the library, it was easy to design an algorithm here. Okay, we started with this and we ended.